We're going to go ahead and work through activity 11.1. In this we introduce rotational motion and how it relates to translational or linear motion. So translational and linear motion are essentially the same thing. Now I want you to take a look at something that's rotating, say like the Earth. If we're out here on the Earth, if we're on the equator, in one day we travel a pretty large distance because we have to go all the way around the Earth and back again. But if we're up on the North Pole, we don't travel very far at all, at least linearly, but we both go through the same angle, right? If I go all the way around the Earth, I've gone through 360 degrees or 2 pi radians. If I'm up here, I've still gone through 2 pi radians. It's just covered a different translational or linear distance, okay? Which brings up radians, and we have to be able to know radians and use radians. And the reason we use radians is because they're a very handy unit. When we measure this angle in radians, then it's easy to get the arc length s that angle corresponds with. It's just r theta. R theta equals s. And so that tells us that we can, if we know the angle something rolls through, we also know the distance that something has moved as long as we know the radius r. So for something on the edge of the circle, this is that distance. For something here, the radius is a little bit less, so the distance is a little bit less. And the reason this is a nice thing to know is because if this was actually rolling along the ground, then as this point rolls down, it covers this much distance, and so that actually corresponds to a translational motion of about that far. Okay. So we know we're going to use radians to discuss how far something has rotated. It'll rotate through 2 radians, 3 radians, 4 radians, whatever. Now, because a radian is defined as actually the distance around the circle of 1 radius, there are 2 pi radians in 1 circumference. C equals 2 pi r. So 1 revolution is how many degrees? That's just 360 degrees. There's 360 degrees in a circle, 1 revolution, 360 degrees. How many degrees are there in 1 radian? Well, we got to think about this a little bit. There's 2 pi radians equals 360 degrees. So if I want 1 radian, I'm going to divide both sides of this by 2 pi, and what I see is 1 radian is 180 divided by pi. Now if you want a number for that, 180 divided by just over 3, right, 3.14, you get about 57.3 degrees. So 57.3 degrees is about 1 radian. It's about 1/6 of a circle. Convert the following from radians to degrees. Well, since we have this conversion factor that 1 radian equals 180 over pi degrees, we can do this. It's a pretty straightforward thing. So we use the conversion factor where we have 1 is equal to 180 degrees over pi radians. So all I have to do is multiply this by 180 and divide it by pi, which is just what we had here, 57.3. 2.5, again, multiply by 180 and divide by pi, and you get about 143 degrees. Now I want you to think about this for a minute. 2.5 radians is since there's 2 pi radians in a circle, that's about 6 radians. This is a little bit less than half of a circle. 143 degrees is a little bit less than 180, which is half of a circle. 5.25 radians, there's about 6 in a circle, which means this is going to be less than a circle. So if we take 5.25 times 180 and divide it by pi, then we end up with right around 301 degrees. So yes, this does make sense. Now if we're going the other way, if we want to go from degrees to radians, then we just have to invert our conversion factor. There are pi radians per 180 degrees. So we take our 110, multiply it by pi, and divide it by 180, and we see 1.92 radians. Alright? Oops, 1.92. I'm not going to do the rest of them. You guys get the idea. Alright, moving on. The general relationship between arc length s, the radius r, and the angle theta is given by theta equals s over r. That's how we define a radian. 1 radian is the arc length divided by r. Solve the equation for s. Alright, so that just means I'm going to move the r over, so theta equals s over r becomes r theta equals s. Now, something to point out about this is a circle, and we have the point here, and the center here. So this is r, this is r, this is theta, this is s. If this circle actually was rolling across the ground, the distance it moves along the ground would be equal to the arc length, because that's how far this thing has rolled. So s equals delta x. if you'd like, how far it's moved. So it says, recall the second kinematic equation for motion along a straight line. Remember, the second kinematic equation tells me delta x equals 1/2 at squared plus v naught t plus nothing, right? If this is x, then this would be plus x naught. All right. So this equation can also be used to describe total circular distance traveled by a point on a rotating object. That's true. Rewrite this equation replacing x with s. So instead of x, I'm going to use s. So I have s equals 1/2 at squared plus v naught t plus s naught. Okay, so just like I said up here, this distance that something is moved along the edge of a circle, we can use s instead of x. If a equals 0 and then v equals v naught, because there is no acceleration, and we use these conditions and the result of step 1 to rewrite the equation in steps 2. So remember, we can replace s with r theta, and we're going to go ahead, we're going to say the acceleration is 0, and so v is just constant. So what I get is r theta equals vt plus r theta naught. Alright, solve the equation obtained in step 3 for v and rewrite in terms of omega. Well, what's omega? Let's jump to this box. Just like velocity is the rate of change of velocity, change in position over time, omega is the rotational equivalent to that. Omega is the change in angular position divided by time. That's what this box says. So if we go ahead and simplify and we solve this for v, what we get is r theta minus r theta naught equals vt. Divide both sides by t and factor out that r, and I get r over t times theta minus theta naught equals v. But theta minus theta naught divided by t is the definition of angular velocity. So I can make this substitution. I can say omega times r equals v. Now if you think about what this is saying, it says if you take the angular velocity and multiply it by the radius, you get the linear velocity, which kind of makes sense because we know if we take the angular displacement and multiply it by the radius, we get the linear displacement. It says recall the first kinematic equation for motion along a straight line. Remember that says v is equal to v naught plus acceleration times time. Write it below, did that. Use the result of step 4 to rewrite the first kinematic equation, which remember we can replace v with r omega. Okay, so r omega, so that's radius times velocity, angular velocity, equals r times omega naught plus at. And if I solve this, well, I don't have to solve anything yet. Okay, let's see. Number 6 says angular acceleration is change in angular velocity divided by time. So remember, acceleration is the rate of change in velocity. It's change in velocity divided by time. It would make sense then that angularly, change in angular velocity divided by time is angular acceleration. So the Greek letter alpha is used for angular acceleration. Now, we are going to have to remember this equation. We're going to use that one, and we're going to solve it for acceleration and then make a substitution. So if we get on to the next page, it says solve the equation obtained in step 5 for a and rewrite it in terms of alpha. So if I grab that equation, remember what I have is r omega equals r omega naught plus at. So r omega equals r omega naught plus at. If I solve it for a, then I'm going to subtract that over. I have r times omega minus omega naught divided by t equals a. But remember, a is equal to omega minus omega naught divided by t. So I can actually make the substitution r alpha equals a. So I have the third rotational analog for acceleration. So if we put all this together, what I have is s, which is really x. So I'm going to put that in there. X equals s equals r theta. I also have omega times, well, let's just write these in the same order. Okay, v equals omega times r, and a equals alpha times r. So if I have the rotational part and I want the linear part, I just have to multiply by the radius. That's all this is saying. Alright, in the first line of the box below, write the three linear kinematic equations. The first one, v equals v naught plus at. The second one, x equals 1/2 at squared plus v naught t plus x naught. And the last one, v squared equals v naught squared plus twice the acceleration times the change in position. For each of these equations, substitute s, v, and a using the basic equations of rotation. Alright, so that means in the first one, v equals v naught plus at becomes r omega equals r omega naught plus, and alpha, remember, or a is alpha r t. Now, we can simplify this because this term has an r in it, this term has an r in it, this term has an r in it, and that gets me omega equals omega naught plus alpha times t. So what we get is the rotational analog of this equation, omega equals omega naught plus alpha t. So final rotational velocity equals initial rotational velocity plus angular acceleration times time. Alright, moving on to x. Remember that's s. Okay. So s equals, whoops, that is s, except that I don't want to use s, I want to use r theta. So r theta equals 1/2 alpha, well, except it says a, so that's alpha times r, t squared plus v naught. Remember v naught is omega times r, it would be omega naught times r, plus r theta naught. Again, what I see is the radius is here, the radius is here, the radius is here, the radius is here. So I can divide everything by r, and I get the final angular position is given by 1/2 the angular acceleration times time squared plus the initial angular velocity times time plus wherever I started, omega naught. So again, I basically just get to replace the x's with thetas, the a with alpha, the velocity with omega, and I have the same equation, it's just in angular terms. I bet we can see how the last one's going. V squared, remember that would be omega squared, except it's omega r squared, so omega squared r squared equals omega naught squared r squared plus twice alpha r delta x. Now that's going to be change in position, so that's going to be delta theta times r. And if I simplify, I have an r squared here, an r squared here, and an r times an r, which is an r squared. So I can divide this by r squared, I can divide this by r squared, I can divide this by r squared, and what I get is omega squared equals omega naught squared plus twice the angular acceleration times the change in angular position. So one more time we see that the angular equivalent is exactly the linear equivalent with all the substitutions made for the angular analogs. So not a huge deal on that. Now there are a couple practice problems on here. I'm going to rewrite those equations. So omega equals omega naught plus alpha t. I'm going to go ahead and I'm going to write this one as change in instead of just final and initial. So change in angular position is equal to 1/2 angular acceleration times time squared plus initial angular velocity times time. And finally, final velocity, angular velocity squared equals initial angular velocity plus the angular acceleration times, or twice the angular acceleration times the change in angular position. Alright, so those same three equations, awesome. The initial angular velocity of a uniform disk is 20 radians per second. Its angular acceleration is 5 radians per second squared. The radius of the disk is 25 centimeters, and the mass of the disk is 2 kilograms. We're not really going to have to worry about that, but whatever. How long will it take to reach an angular velocity of 80 radians per second? So I know omega naught equals 20 radians per second. I know its angular acceleration, alpha, is 5 radians per second squared, and I know the radius of the disk, r equals 0.25 meters, if I care. How long will it take to reach an angular velocity of 80 radians per second? So our final angular velocity, it says, is 80 radians per second, and I want to know a time. So I have final velocity, initial velocity, acceleration. I want time. I'm going to use the first equation. Omega equals omega naught plus alpha t. 80 equals 20 plus 5 times t. Subtract that over, divide, and I get t equals 12 seconds. So it's just like using kinematic equations linearly, we're just doing it translationally. What is the linear speed of a point on the rim when the disk has an angular velocity of 80 radians per second? So what this is asking for, the linear or translational speed of this thing, is how fast is a point on the outside of this disk actually going? If it was, if it was rolling along the ground, how fast would this thing be going? So the linear speed is v, and remember v is equal to omega times r, and since omega is 80 radians per second, what I have is 80 times 0.25, which is just 20 meters per second. Remember that 0.25 is the radius from up here. What is the linear acceleration of a point on a rim? Same thing. Linear acceleration is angular acceleration times radius. So I get 5 times 0.25, and I get 1.25 meters per second per second. Not meters per second per second per second. All right. Final thing, through what angle does the disk, oh, nope, two more things. Through what angle does the disk turn while accelerating from rest to 20 radians per second? So our initial velocity, omega naught, is 0. Our final angular velocity is 20 radians per second. I'm going to assume that the acceleration is still the 5 radians per second per second. And it wants us to figure out through what angle the disk turns. That is, it wants a change in angular position. How many radians did it turn through? So I'm going to use that third equation, omega equals omega naught squared, omega squared equals omega naught squared plus 2 alpha change in angular position. Final is 20, so 20 squared equals 0 squared plus twice 5 times change in angular position. So 400 equals 10 change in angular position, and our change in angular position, or how many radians is rotated to, is 40 rads. Yeah. So 40 radians, we're good. How far will a point on the rim travel while the disk is accelerating? Now I actually want to know a linear distance, how far something has gone. Well, since I know theta times r equals arc length, which is really how far it moved, then I can just take my 40 radians times the radius, 0.25, and I get a distance of 10 meters. So if we know linear things and angular, and if we know the radius, we can go from angular things to linear things. So using these equations is pretty straightforward. There are a couple more problems that you guys can work through, get this activity done, and then we will work on a lab and what actually causes angular acceleration.